Good morning and welcome to the ATCO SpaceLab Speaker Series. My name is Kelsey Stephen and I am a member of ATCO's Transformation Team. I'm pleased to be your moderator today. While this is a virtual format, I ask that you join me for a moment of reflection on the meaning of place, to recognize the significance of the various traditional, ancestral, and unceded lands on which we are located. With gratitude and reciprocity, I acknowledge that I live and work in Treaty 7, the traditional territories of the Niitsitapi of the Blackfoot Confederacy, comprised of the Siksika, Kainai, and Piikani nations, the Tsuut'ina Nation, the Ithaca Stoney Nakoda, including the Chiniki, Bearspaw, and Goodstoney First Nations. This land is also home to the Northwest Métis and to the Otipemisiwak Métis government, Nose Hill Métis District 5, and Elbow Métis District 6. Today's speakers join us from Sandia National Laboratories in Albuquerque, New Mexico. Albuquerque sits on the traditional homelands of the Pueblo of Sandia and is home to the Pueblo, Navajo, and Apache peoples of New Mexico. Today's lecture is a one-way video and audio format. Please ask questions by using the Q&A button at the top of your screen, and we will ask questions at the end of today's lecture. I will now hand it over to my colleague, Andrea Kleiber-Langen, to introduce our speakers.
Thank you, Kelsey, and welcome everyone, and thank you for spending time with us today. We're excited to be joined by Drs. Eric Cyr and Brad Theilman from Sandia National Laboratories. Dr. Cyr is a principal member of the technical staff and holds a PhD in computer science from the University of Illinois. His work focuses on applying machine learning technologies to science and engineering problems. Dr. Theilman is a postdoctoral appointee and holds a PhD in computational neuroscience from the University of California, San Diego. His research focuses on brain-inspired neuromorphic algorithms for scientific computing. Today's speakers will share their expertise in neuromorphic computing with us. As I'm learning, the design of neuromorphic systems is motivated in part by the way actual neurons signal each other in the brain. The first part of today's discussion will show how the programming model for these systems is motivated by concepts from neuroscience. The second part will discuss Dr. Cyr and Dr. Theilman's work in implementing a neuromorphic model for scientific machine learning. We are excited to have you both share your work and knowledge with us today, and we look forward to learning from your expertise. Please go ahead.
Oh, thank you very much for the introduction and the opportunity to give a talk here today. We're really excited to share kind of our work as we're both getting into this. I mean, Brad's been doing neuromorphic computing for a while. This is a new area to me, but bringing this with the scientific machine learning has been a really exciting part of a collaboration that we've kind of had through the CCROGS project, which we'll talk about a little bit. All right, so to start with, neuromorphic computing is really motivated, as mentioned earlier, by the brain. And so what's so interesting about the brain? Well, animals require significant computational capacities to survive in some really complex environments. So like one of my favorite things here is like, it feels like every day I find a new example of a animal using a tool or something like this. And in this case, it's a crow using a stick. I think that's pretty amazing. And that's a very complicated mental activity, computational activity. Same with kind of interception. You know, this eagle has to see a trout or a salmon and then swoop down and grab it. I think that's pretty complicated activity. And then the intricacies of a spider web and its complexity, building this kind of complex geometry in a hostile environment, potentially hostile environment. And so evolution has really kind of enabled all of this, and some of the goals of neuromorphic computing then are to kind of be able to reflect this in computing hardware and take advantages of some of the ideas that have been generated by evolution itself. So, you know, there's several paradoxes, right? So we have these amazing supercomputers at Sandia. We have giant HPC machines, we have GPUs and all these great things. But what we realize is that there's still things that are kind of historically difficult for computers to do, like object recognition and learning, complex movements, and language, and decision making under uncertainty. These are all things that are very difficult, and yet nature seems to do them seemingly easily. So, only recently with the development of neural networks and machine learning have some of these things really we've been able to really achieve these kind of in kind of the complexity that nature kind of does this regularly. So let's see. And so there are other examples, music and art. These are all things that we're not good at simulating despite amazing amounts of computational power. So then we can ask the question, what is the major difference, okay? And it turns out the brain and computers, while, we often make the analogy that a CPU is like a brain, they really look nothing like each other. A central processing unit would take in some input and have some sort of computational architecture, some floating point units, some registers, a memory to go out to, and then an output device, so a disk or monitor or something like that. Where a brain is much more, has a much different structure, okay? And when we see that, one of the greatest disparities is really in the energy usage. An amazing thing is that the whole human brain only requires 20 watts. To me, this is amazing. If I think that like 5 years ago, I was plugging in an incandescent light bulb in with 50 watts, right? And that takes way more power than the brain. And if we then compare that even worse to a GPU or a supercomputer, we see that there are orders of magnitude different in power consumption. And this is becoming more relevant, particularly with the machine learning. As machine learning kind of grows, we're seeing the stress on data centers in terms of their power consumption. We see people talking about the power needs of data centers. And so coming up a way with reducing that power footprint while maintaining a computationally effective tool is, I believe, a very important frontier in computational science and computer science in general. But really the challenge here is that our understanding of biological computation is still incomplete. We're still learning a lot about biology and how it does its work, despite kind of the nominal motivation of things like neural networks, which I've pictured here, as a biologically inspired object. And so what neuromorphic computing really is about is to try to come up with good models, a model of a hardware model that's kind of motivated by the brain. And to build special architectures that kind of focus on this, to the type of computations we'd like to actually perform in this context. And we'll talk about, throughout this talk, kind of how this is realized, and at least in the current kind of state of the art of neuromorphic computers. So one thing I want to say is much of this is motivated through our own inspection of an existing kind of neuromorphic hardware platform. The Intel's Loihi 2 is an actual existent platform. We'll see a picture of it at some point later in the talk, that we can actually run real simulations on. And so it's not a fictional platform. This is not speculative. We have real hardware we can try these algorithms out on, and that's going to be an important aspect. And I think that our architectural and abstractions and algorithmic abstractions reflect this particular hardware. So to start with, where does this neuromorphic computing get kind of its idea? It starts kind of at the very basics of the brain, which is a neuron. The brain is a connection, a collection of interconnected neurons. And each neuron has a nucleus. It has dendrites, and which kind of are fingers out to neighboring neurons. It has synapses that provide this connection between two neurons. And then it would take in that signal and bring it down into this axon, and then send it back out to its neighboring neurons. Okay, and I'll go through that again. So the question is, this is like a computational unit, but what is the signal and what does that look like that it's actually receiving? So I kind of think of it in this kind of workflow sense. So we have a cat, and maybe we see the cat. Okay, so the question is, what is this? Well, that image is turned into some sort of electrical signals. And so you could think about the electrical signals as binary signals, where each neuron might get a particular sequence of input signals, where they are, it's a discrete binary signal over time, okay? So what this is called is a spike train. Each of these black blocks, which indicate a one signal or an on signal, is known as a spike. And so we then feed these into the neurons in the brain, okay? But the brain then converts these into these signals and sends them down into the neurons, okay? And this is then distributed over the whole thing. And in fact, between neurons, the exact same kind of information structure is passed between neurons. So there would be, this axon would have a sequence of spikes on it, and they would be passed to the neighboring neurons to then do some sort of processing on. This all comes out then as a set of output signals, again, and then we interpret this set of output signals as, say, a cat, all right? So you can imagine there's several different steps. There's this encoding step where we take the image and then convert it to a set of input signals, and this decoding, and then we process it. We do some computation to determine it's a cat, and then we convert those output signals and decode them into what we understand as a cat. So computationally, we will have to do each of these steps. All right. One unique aspect of this is that the signals aren't all the information in the brain. Okay, so the neuron itself can actually maintain state, so it remembers, so to speak, information about previous spike histories. Okay, so it's going to be able to use that in computing the end output signal. Now, the real an interesting thing, and why this is important, is that the on-off nature of spikes is really a big source of energy savings. Okay, so if there is no spike, if there's a set of white, like these set of white time points here, that requires very little energy to transmit, because we're just basically sending out zeros. So then we can ask, what is the life cycle of this neuronal signal? Okay, so we have that signals are going to be received through these synapses. Okay, so it's going to be on or off. The dendrites are then going to aggregate these synaptic signals to a kind of a singular signal that is received by the nucleus. And then I'm going to just call this magic, because this is where the magic of the neuron is. It's going to produce a new signal. It's going to transform this thing into a new signal and pass it down the axon. And then it's going to then eventually reach the dendrites and then propagate outwards to neighboring neurons. So we can then take a full kind of a step back, and we looked at a single neuron, but we can actually look at this then as a network of neurons, say a neural network, so to speak. And so these, again, these input signals are passed in, they're passed along each neuron, and then they are actually transmitted in a converted form along each axon until we reach the output, right? And this isn't just a theoretical construct, right? This is actually can be measured. So Brad, in his degree, did this amazing thing for me as a computer scientist, but he had actual experiments where they would interrogate, hook up sensors to the brain of songbirds, and then actually map out the kind of neuron responses throughout the brain. And so here's a picture of this, a movie of this actually happening. And so you can actually see the spikes in this setting. You can see like where these like little yellow things are spiking. This is a very concrete evidence that this, at least at some level of the brain has this kind of activity. How we then organize that activity to do useful computational work is really the problem for us as computational developers in algorithm. And we'll get to that. All right. So I've talked now about the neuron and the brain and the neuron networks of neurons. But what I would like to do now is transition to where we're actually doing computing. So what is a neuromorphic computer? Well, it basically replaces a single neuron by a processor, a computer processor, okay? And they have the same kind of structure. So the input here, the thing that takes in the spikes would be the synapse, okay? And we might have multiple of these synapses that talk to neighboring neurons. So here you see this neuron has 3 synapses. It's talking to neighboring neurons in this picture. And then we would have dendrites, these that aggregate the signal. And mathematically, this is going to be an accumulation step that happens in this little gray box, which is representing an accumulation processor. And then we have our magic, which is where the neuron transfers that accumulated kind of information into a signal that is then passed outward to neighboring neurons. And so we can then imagine that these things are networked together like this. So we have these input neurons, they get raw data from the input. And then we would then aggregate them in these little gray boxes here. And it's passed through the processor that aggregated the result. And that produces some sort of signal, which is then put back on these wires. And that produces an answer. All right. So I'm gonna just I'll probably repeat this now a couple of times just to get a sense of this. So we have input spikes, okay? So this time-dependent history of on-off signals coming into an accumulator. That accumulator aggregates those spikes and produces what's called a current. Okay, this is very much based on the biology of a neuron, the language here. And it produces this aggregated set of signals and passes those to the processor. The processor then acts on those and produces an output set of spikes. So we can take a closer look at the parts. And here I'm trying to get to a little bit more mathematical structure so we can start to think about structurally, how would we look at algorithms for this type of architecture? And so the accumulator, because it takes a bunch of spikes, so what we have is a bunch of spikes. Those are represented by this vector x. It would be a 0, 1 at a particular point in time vector. We'd multiply it by a matrix, and that would naturally accumulate, okay? That accumulated value is then passed to the processor. Okay, so we would have each row of this product be passed to a processor, which is then processed by some sort of potentially nonlinear function, sigma, and then that produces spikes. All right, And there's several different things to think about here. The accumulator is really just weighting each input spike and producing a sum. And it outputs a signal current, which might be a floating point value or an integer value, okay? The processor, well, it has a fixed amount of state. What does that mean? Well, I showed you these pictures of computer networks of processors. Each processor is only allowed memory access to what's coming into it and what it stores internally, okay? So that's O of 1. It doesn't care about how many processors are in the network. All it knows is about what's coming in, what's going out, and what it can store locally. And that's a very small amount of memory associated with a handful, say 5 or 6 registers. And so there's really no global memory access for this. An interesting architectural thing that you can do with this picture is you can actually decide that, hey, my processor can actually send itself a message in form of the spikes. And so now we can actually make these processor systems recurrent. And therein lies kind of an additional level of complexity that we don't typically think about in computing. But I think it's a really important aspect, and we'll kind of hint at that as we go forward. So let's kind of really kind of dig into this mathematical abstraction a little bit more. Mathematically, what do I see? Well, this accumulation is produced, if we have these signals, x1, x2, x3, it's producing a current, A times X equals U, where U2 is, say, the second component of this. And there are neighboring processors that are processing the U1 current and the U3 current. All right, so that's the first step, this matrix vector multiply. The second step is actually the processor, and it's producing a nonlinear response. Okay, so it's going to take, so for this processor, which is processing on the U2 current, it takes U2 as input. It has some local state, O of 1 sized local state, and then it takes a nonlinear activation and produces a new signal X prime. Right? And then there are neighboring processors in parallel doing the same thing. And so, you know, we can then think about this whole system as kind of being parameterized then by a set of input spikes, which defines the state of the computer system, or the response and the input state of the computer systems, a matrix that maps those spikes into currents for each neuron, and then a current vector, and then the number of processors. And each processor then has its own little bit of processor state. So mathematically, then I look at this kind of as a very relatively simple set of functions. And I don't think this is surprising if we're familiar with neural networks. It looks very much like a neural network. But we would have a set of spikes at any given, say, time point, say, coming in as X. We have a weight matrix, A, which is potentially learnable. And we might have bias vectors, okay? And that's going to convert the input spikes into a current. That's going to be acted upon by a nonlinear component-wise activation. That's because each processor only has O of 1 memory. And each processor, each neuron in this case, has a particular state associated with it. So it looks a lot like a neural network, but there's some important differences that I haven't quite touched on yet. But in the hardware itself, the low E hardware itself, all of these quantities, the spikes, and then the current, all of this is limited to a finite number, say a small number, say 24 or 8, some number of bits of information. So the current is limited in its precision. And so that's going to be a big difference. And really, that's an important part for power consumption, right? So floating point units require a lot of power and also have a lot of require more silicon real estate. And so this is important to control the actual power needs of the neuromorphic computer. So in the end, what do we have? What do I like to think about? I think about a system that kind of looks like this. We have time-dependent spikes, these input spikes here, and each time step corresponds to neuromorphic computer cycle. I think there are some people that like the notion of asynchronicity, but for our purposes, I'm thinking about it as synchronous because it's a little bit easier to reason about. And so we can then take the spike state of the network, add to it some sort of operator that brings the input spikes into the network as current, and then we can produce a new spike state for the neuromorphic hardware. And so we end up with a process that takes, for a number of processors, takes input spike trains and produces output spike trains. All right. I want to get into just one little detail before I hand this off to Brad. And that is this notion of component-wise activation function. These component-wise activation functions, these sigmas, are, as I said, they're very specialized objects. They have little bits of local state that persist between time steps, okay? And it has to produce the output stream. The most canonical example of this is this leaky integrate and fire model. What the leaky integrate and fire model does is it takes a current that comes from this accumulation step and produces a spike, a set of spikes that are associated with the kind of response it sees. The way it does this, it actually solves an ODE underneath the hood. Mathematically, you can think of it as an ODE. And it's heavily motivated by the response that we've seen in real neurons. And so the leaky integrate and fire model has many kind of learnable parameters. They have an internal state associated with this potential VI. UI is the input current, okay? And then we have learnable alpha and B parameters. And we produce, with this expression, we produce a simple update for a provisional current. At this point, it's basically a linear function. What we then do is we look at this potential and we say, oh, has it achieved a particular voltage? Okay, so basically it's modeled as a potential. So this is a voltage that it's expected to threshold that it's supposed to meet. If it doesn't, if it's below the voltage threshold, that seems backwards, we emit no spike, okay? So basically you can see here, this is like this V parameter. We get to this point based on what the input spikes. If we're below this threshold, we do nothing, okay? There's no spike emitted. And then because of this alpha parameter, there's actually a relaxation rate. This potential is allowed to decay. And then it sees the next potential and it jumps above the threshold and emits an output spike. And then it resets itself to 0, okay? And we do this repeatedly, and that is what kind of describes this sigma parameter, this sigma activation function. All right, so kind of to give a summary before handing off to Brad, you know, the challenges of neuromorphic computing is there's really no global memory access. That's a real issue. But I think it's also a source of the power of it, because it leads to kind of highly parallel systems. We have less kind of computing infrastructure that has to ensure that messages are delivered at any point in time and in the hardware space. There's also low precision and fixed point computations. This was a big surprise to me. It feels like we're moving back to the 50s and 60s in a computer science perspective. There's limited expression. I didn't get into this, but these little processors, they're very simple computers. And so there's some things that don't actually exist within the assembly language. In particular, there's no divide. This was also a huge shock to me. And we figured out how to work around this eventually, but these things are very difficult to deal with when you're first approaching them. And then mostly, I think it's this totally foreign, unfamiliar computing model that we're still kind of coming to terms with and grappling around. But I think it has some real advantages. Low power, it's highly parallel. It's cool because it's modeled after the brain. And so there's nice symmetry with neural networks as we're getting into more and more machine learning. And for me as an algorithm developer, this is the last point. I think it's a really exciting time for new algorithms. And so I guess with that, I'll hand it over to Brad and let him take over. Thank you.
All right. Thank you very much, Eric. Yeah, back one more. There we go. All right. So, so Eric gave a very strong overview of neuromorphic computers generally. And what I'd like to do is dive into a specific example about how we are developing algorithms to solve a specific kind of scientific machine learning or set of scientific machine learning problems. And so I'll start by describing what we mean by scientific machine learning. So as you're probably aware, machine learning has exploded in a variety of application domains, but one thing that we're particularly excited about is the application of machine learning to computational science problems. The methods that have succeeded in artificial intelligence are inspiring new kinds of numerical algorithms for solving the kinds of numerical problems that we encounter in scientific computing. And one particular advantage for these kinds of algorithms are what we call data-driven discovery of scientific principles and models. So before, we would have to start with a set of physics equations, and we could write them down abstractly, and we could solve them. But it was comparatively difficult to make contact with real experimental data. What machine learning models allow us to do is to combine the physics that we know with the actual measurements that we take in the real world and gain new kind of scientific insights by training machine learning models that are adapted to the physical problem of interest. And from that, we can garner insight about about scientific challenges that were difficult to surmount in the past. So there are scientific machine learning is exploding in popularity right now, and there are a number of different models and approaches. Two of the most fundamental that I'm going to bring up for now are what are called physics-informed neural networks on the left and deep operator networks on the right. And for most of this talk, I'm going to talk about physics-informed neural networks, although we are starting to get sort of deep into neuromorphic approaches to deep operator networks, but that's sort of that work is still kind of ongoing, and we're still solving a few problems there, but we're close. So for our purposes, physics-informed neural networks are very similar to conventional neural networks that you might encounter in machine learning, where we have a sequence of layers of neurons that communicate with weights. And you're trying to transform an input space to an output space. But what differentiates them is that we augment the training of these physics-informed neural networks by our knowledge of the physical equations that describe phenomena of interest. So where in conventional machine learning, we just have a data set and we hit go and train so that we make sure that the error kind of decreases over time. In physics-informed neural networks, we augmented that training with extra terms, which I'll describe, that sort of incorporate our knowledge about the physical equations, so that as the model learns, it sort of bakes in the structure of the physics into the neural network itself. And this is actually extremely advantageous because now we can produce models that incorporate our prior knowledge of the physics, but also the experimental data that we can measure in the lab. So I'll just briefly touch on deep operator networks. So deep operator networks are sort of a natural generalization of the pin idea. So in physics-informed neural networks, we learn a single solution to a partial differential equation that describes some physical phenomenon. Deep operator networks kind of duplicate the deep network part, but separate the roles so that we can now learn not just one solution, but a whole family of solutions. So if I were to want to model, say, temperature over some domain, I start by specifying, where all of my heat sources are, and then that defines an equation. And if I solve that equation, I get the temperature of whatever I'm trying to model. So the physics-informed neural networks would solve that for one specific set of heat sources. But in deep operator networks, I now have an extra network where I can specify different different kinds of arrangements of heat sources or inputs and get the solution for any particular one. So they're strong relations, but physics-informed neural networks are sort of like the foundation for a lot of these scientific machine learning approaches and what I'll be talking about for the rest of the talk. So if we move to the next slide, I think, oh yeah, I apologize. Yeah, I had my slides kind of disordered. I wanted to describe a little bit more about specifically how these physics-informed neural networks are constructed. So if I were to describe what a general physics model looks like, it would look like the equation at the top left. I have a variable u that represents some physical quantity of interest. Could be a number of things, but it's probably easiest to imagine something scalar like temperature. So u represents the temperature over some kind of system that I want to study. And u sub t represents the rate of change in that temperature, how that evolves through time. And the n here is deliberately vague. It's supposed to represent all of the physics that governs how that temperature evolves. So it's obviously going to be a function of the temperature itself, but it may also be a function of other parameters, lambda. And this equation just represents the condition that the physical temperature that is observed solves this equation where the time dependence and the rest of the physics sort of balance out to zero. This is a convenient way to specify how physical quantities evolve. So the way pins work is we make the guess that our function u that we're trying to model can be approximated with a deep neural network. And so I think most people at this point are familiar with the architecture of deep neural networks, but we have a sequence of layers of neurons that map an input space to an output space. In the pins case, the input space is going to be a set of coordinates, x, y, z, and t. So this gives us our position in the object and then the time at which we want to evaluate it. And the deep neural network is going to map that to a quantity u that represents the temperature or whatever quantity that we're trying to model that we would like to solve the equations that govern its evolution. So on the right, I have just sort of a sketch of the construction of the loss function that is specific to pins. Most neural networks incorporate a term in the loss function that we call the mean squared error that represents the difference between the network's output and the data set that we're trying to train on. And this is no different. So we may have some data about measurements of temperature in our example on some object under some conditions. And we want to make sure that our neural network recapitulates that data set because that's what we know to be true. What separates pins is we add an additional term to this loss function that is now determined by the physics equation that we define in the top left. And I represent that as this f here. And so this MSE sub f term represents the kind of the departure from the neural network from respecting the physics. And so if we combine both the data loss and the physics loss, we get a new loss term that I've kind of illustrated at the bottom. And if we train our network with respect to this loss function, then as the value of L decreases, the network will start to approximate both the data and it'll start to approximate the physics. So if we move to the next slide, we can see some examples of this. So I have two examples that I think are kind of interesting. On the left, we have a physics-informed neural network approximating the solution to the Schrodinger equation, which is obviously important in physics. At the top, you can see the x's marked data points that were used to train the model. But other than that, the only thing that went into this was the definition of the Schrodinger equation itself in that specific form of u sub t plus n equals 0. And what we can see at in the bottom frames is that the predictions generated by the pin very closely approximate the exact solution that we've gotten through traditional means. And so this demonstrates that the network can learn both to fit the data points, but also respect the physics. Similarly, on the right, I have an example where a pin was trained on the Navier-Stokes equations for fluid flow. So at the top, I have a very canonical sort of Navier-Stokes problem, which is this flow around a sphere or a disk or rod or something, generating these vortices, which are very characteristic and typically hard to model. And we can take data points from a measurement or evaluation of that flow and build a data set in the middle here that we can train a physics-informed neural network on. But importantly, we can also include the Navier-Stokes equations in the training itself. And one of the things that we get out of this is that not only can we model the solution, but we can extract the actual parameters that generated the data. So things like the viscosity or other fluid parameters that we may not know ahead of time, the the pin can, through its training, through both the data and the physics, can identify what the appropriate parameters are that describe the data. And so we learn something about the physical system from training this network. So these, I think, give kind of compelling reasons why scientific machine learning is an exciting advance in our understanding of methods for scientific computation. And there are a number of cases where we'd like to take these insights and deploy them in places where a supercomputer or other large GPU or something like that is just not feasible. So this motivates our search for neuromorphic counterparts to these scientific machine learning algorithms. And so what Eric and I have been doing has been trying to translate these networks to specific neuromorphic hardware, in our case, Intel's Loihi 2. So if we move to the next slide. Loihi 2 is a neuromorphic chip, a neuromorphic architecture produced by Intel that is really exciting because Intel has started to scale this to some of the largest kind of neuromorphic computers that we've seen so far, actually. And one of these in particular is called Hala Point, which we believe to be the world's largest neuromorphic system. This is basically a supercomputer, but it's built very unconventionally. It follows the principles that Eric described in his overview of neuromorphic computing. And so if we can talk a little bit about the numbers that we're dealing with here, this system has roughly over 1 billion artificial spiking neurons and 128 billion synapses. That's the largest neuromorphic computer that we know of. And to put that in comparison with the biology, that's on the order of magnitude of, say, an owl brain. It's fast. So Eric mentioned that one of the things that is promising for neuromorphic computing is that all of these neurons are acting in parallel. So you have 1 billion neurons that are updating themselves in parallel, meaning that the system can achieve over 300 trillion synaptic operations per second. And an equivalent memory bandwidth of something like 16 petabytes, which is pretty wild for a system of this size. And importantly, it's energy efficient. So Intel has measured a performance of around 15 tera operations or TOPS per watt, which is very, very exciting because that's many orders of magnitude better than some existing computer platforms today. And on the right, I have a picture of me with some of my colleagues when we received this system and sort of unboxing and setting it up for the first time. It was a very exciting day to be able to kind of see this, very unique and special system kind of come to life. So I'll talk a little bit more, put a little bit more detail about the Loihi 2 architecture itself if we move to the next slide. So these, on the left, I have pictures of the actual Loihi 2 chips. And these are, you can see 4 of these rectangular chips arranged on this circuit board. And these are the actual processors that implement the spiky neural networks that Eric described. Now, within each one of those chips, we have an architecture that's shown on the right. So within each one of these chips, we have a mesh of what are called neuromorphic cores or neurocores. And these are the pieces of silicon that contain the processors that Eric talked about that implement the individual neurons. And then between each core, we have an on-chip network that is highly optimized for routing these spikes, as he described, between cores and between neurons. And so this gives us a mesh on a single chip of a bunch of neurons. I think each chip can accommodate up to about 1 million neurons. And furthermore, the chips can communicate with each other. So a spike from a neuron on one chip can be routed and translated across the entire system to a spike at the neuron on the other side of the system. And so this allows us the flexibility to construct really large spiky neural networks and investigate their kind of algorithmic performance. But as Eric mentioned, the computational model that Neuromorphic is built from is significantly different from the way conventional computers are architected. And this has required us to kind of step back and think through numerical problems for these algorithms that we normally didn't have to think about. And I'll describe that here in a second. And it's kind of exciting for me because the constraints that these systems impose on us while allowing for things like energy efficiency create a lot of exciting new mathematical problems for scientific machine learning. And that's kind of my interest in this, is it's fun to solve these kind of problems. So now I'd like to move on to the next slide and talk about a spiky neural network implementation of pins. What we're doing right now is we're ignoring learning for the moment, and we're trying to translate a previously trained pin model to a spiky neural network. And this is actually a very non-trivial task. To begin, we have to define what Eric called the magic in the individual neuron processors that make up the neuromorphic chip. And so that's given by the equations on the top left. This is very similar to the leaky integrate and fire neuron that he described. So I have an equation that describes the update of a state variable V, this membrane potential, as a function of incoming spikes that are weighted by a weight matrix. You can see the sum there. And then there's a decision rule where based on the value, the numerical value of that membrane potential, we either emit a spike of one sign or of a negative sign or not emit a spike at all. And so starting from this assumption that these are the dynamics of our individual neurons, the task for us is to describe how they are supposed to be connected, what the numerical value of these parameters should be so that the spikes that they produce approximate the function that we want, and how do we implement that on the hardware. And this is the first problem is actually really challenging and counterintuitive, because representing information with spikes is very different from how we normally represent information in a computer. Spikes are not, it's not like we have a memory location that we can just refer to as a variable and say that value is 24 or whatever. Instead, the information is represented over multiple neurons and over time. And even though we know a lot from neuroscience, there is no canonical way that information is represented in spikes. There's a lot of freedom in determining how you represent information in a spike train. And so we've taken a particular approach that seems to be relatively productive, where we can convert a spike train to a numerical quantity by averaging the number of spikes over time. So I have an example spike train in the middle here, and each one of those tick marks represents a spike. And to convert that to a numerical output, I have a sort of an average, a numerical average over time to give me the value of U given a spike train. And some of our collaborators, applied math collaborators at Brown University, have proven some theorems that under these assumptions, the spiking output that we can produce by these neurons approximates the conventional activation functions such as TANH that we normally use in neural networks. So this gives us a grounding where we can start to translate the math that we know from conventional machine learning to this unfamiliar spiking domain. And so we can take a trained physics-informed neural network and convert the parameters in such a way that the spikes preserve the mathematics that we expected to implement. But that's not the end of the story. So we have to move on to the next slide and talk about specifically mapping this new spiking map onto the hardware. As Eric mentioned, this hardware has some, kind of like physical limitations about how data is represented. In particular, all numerical quantities are represented in fixed point, which is very different from the floating point that we're used to. So we have to sort of translate the conventional parameters to fixed point representations in such a way that we can preserve as much accuracy as possible. And I'm going to describe, I know there's a lot of equations on this slide, but I'm going to describe generally how this goes. The first step is to introduce these barred quantities at the bottom left that represent fixed point versions of our conventional floating point quantities, like the membrane potential, the bias, and the weights and thresholds, and all of these parameters. And associated to each one of those fixed point quantities is a scale factor given by 2 to the s. So we have a power of 2 scale factor that determines sort of the magnitude of these quantities. And once we have written this down, we can sort of back substitute the definition of these fixed point quantities into our equations that define our network that I put on the last slide. And we can do some algebra. So we can, replace our floating point weights with fixed point weights with 8-bit precision and so on, and sort of, go through the algebra. And we're left with the equation at the bottom, which describes the fixed point mathematics that corresponds to the floating point dynamics that defines our neural behavior. And this is the equation that's actually implemented on the chip. So once we have this, we can take this and translate it into a specific sort of assembly language that defines how individual processors in the individual neuron processors in the chip operate. And now we have a way to define a network on the chip that implements the mathematics of the pins. So if we go to the next slide, I'm going to set up sort of the first thing that we tested. We're very interested in comparing the energy efficiency gains that we get on neuromorphic hardware versus the accuracy that we're able to get. So, because the precision of the parameters is limited, we're going to incur some sort of accuracy cost. But we're exploring this trade-off between accuracy and energy, meaning that, the efficiency gains in solving these networks on the hardware may outweigh the sort of, hits that we take on accuracy by having to constrain our network parameters to certain bit widths. So the experiment that we set up was to kind of compare 2 different networks to each other. We implemented networks on Loihi 2 that had 8-bit weight precision, and then we implemented similar networks on the same chip that had expanded precision 16-bit weights. And we did this by sort of playing a trick. We doubled the number of synapses so that half the synapses represented the most significant byte and the other half represented the least significant byte. And we measured the accuracy and efficiency of each of these models to sort of map out that trade-off. So if we move to the next slide, I can share some results from the actual chip itself. So what we did here was we looked at a physics-informed neural network that was trained to solve the Poisson equation on a square. So this is the equation that describes, for example, the steady-state heat conduction in some domain. And so you can think of this as like a map of the temperature of some disk or like square of metal if you heat it constantly, uniformly over its entire domain. And we use this example because it has an analytic solution, so we know exactly what the answer should be, and this allows us to kind of get a baseline for these neuromorphic algorithms and how well they compare. So on the top left of the set of panels on the right, I have what this target function should look like. Next to it on the right, I have the floating point implementation of the spiking pin. So this represents the sort of simulated, this is what our math suggests that we should get. And on the bottom two panels, I have the output from the neuromorphic hardware itself. And on the left, I have the 8-bit version. On the right, I have a 16-bit version. And you can see that they both very closely approximate the floating point version that we expected to get. Of course, the 8-bit version shows a little bit worse performance, but it's still, if you look at the RMS accuracies on the left, it's still close enough for us, to consider this a promising solution approach for these kinds of problems. And so now that we had the sort of accuracy results, we wanted to go and profile the actual energy consumption that these chips use to solve these problems. And what I'm plotting here is the energy per inference. So for each point in our domain, an inference represents the computation of the temperature at that point. And one of the advantages of these large-scale neuromorphic systems is that we can duplicate this PID network many times over these chips. That means we can run, a number of replicates in parallel. And this allows us to do many inferences at the same time, which increases our throughput. Now, the energy per inference is the power that was consumed by the chip during the period that we ran it, times the number of inferences that we were able to achieve through that second. So if we can increase throughput and decrease power, we can get a very low measure for, we can get a very low measure for energy per inference. And this allows us to demonstrate the sort of efficiency of neuromorphic hardware for solving these problems. And so what I've plotted here on the right is the energy per inference in microjoules for both the 8-bit and 16-bit models. And what we can see is that in the red curve, as we increase the number of replicates, the parallelization factor of these networks on the chip, the energy per inference decreases, which is very encouraging. I mean, it's already extremely low. We're in the microjoule range, tens of microjoules, which is very impressive. Comparing it to the blue curve, which represents the 16-bit model, we can see that we're still in similar orders of magnitude until we hit a point where the number of synapses requires us to kind of split the network across multiple chips. And mapping these networks physically to the locations that they occupy on the physical chips actually incurs significant. It's actually a tricky problem because you want to make sure that neurons that communicate to each other are as close as possible physically to each other, because these spikes have to route themselves through the network. And if we can make them as close as possible, then we can kind of reduce the energy that's required to transmit a spike from one point to another. And this is still something that we're trying to actively solve in neuromorphic computing, because it's a difficult mathematical combinatorial problem. And so what we can see here is that the significant energy hit that we see when we reach that threshold where the network has to be kind of split up in a more intelligent way than we were doing it initially. But these curves were, when we first got them, very encouraging for us, because it shows that we can start to solve these physics problems with a significantly low energy per inference. And even though the model that we're solving is simple, the Poisson equation, the architecture of the pin doesn't change for different kinds of physics that we wanted to learn. That's one of the advantages of machine learning. So even though this is a simple problem, we expect that these sorts of energy or efficiency gains will hold as we move to more complex problems. So I'd like to switch gears a little bit and talk about a completely different way to solve similar problems using neuromorphic. As Eric mentioned, the fact that this computational paradigm is so different from conventional approaches means that there's a lot of opportunity for exploring new kinds of algorithms to solve problems that we wouldn't necessarily think to use before, because the conventional computers that we use are extremely poorly suited for those particular approaches. One of these kinds of approaches is what we call random walk computations. So a random walk is where you have an agent or a walker, we call them, that's at a particular point at a particular time, and as time moves on, it moves to a different position, but the direction that it walks is a random variable on each time step. So the actual trajectory that this walker will take is probably is a statistical thing. It's not deterministic. And as you know, computers conventionally are extremely deterministic, and simulating random walks is extremely computationally expensive for conventional computers. However, and this was not work that I personally worked on, but it was actually work that got me interested in neuromorphic computing originally, and was done by people in our group at Sandia prior to my arrival, was they realized that these sort of local computations and nearest neighbors interactions that neuromorphic computers are good at are actually extremely well adapted to these kinds of random walk processes. So what they did in this paper that came out in Nature Electronics in 2022 was define a spiky neural network using the LIF neurons that Eric described that emulated random walk computations directly. And so at the bottom left, I have an example of a simulation that shows what this looks like. The sort of the heart of the analogy is that we can imagine the walkers in the random walk computation as spikes in the neuromorphic mesh. And so when a spike is received by a neuron, the neuron has a local random number generator, and it can generate the random draw that defines which direction that walker will move next. And then once that decision is made, that's part of the magic that Eric described that's happening within the neuron. That spike can be transmitted to the next neighbor in whatever direction it needs to go. And so the bottom left shows a set of spikes that are sort of diffusing across a donut mesh or a torus. Now, why we're interested in this mathematically is that one can show that the mathematics that describes these random walk trajectories is actually equivalent in some sense to the PDEs, the partial differential equations that describe certain types of diffusive phenomena in physics, in particular, heat diffusion across an object. So we can map the solution of a PDE to a random walk process and then implement that on a neuromorphic computer. If we go to the next slide, this is kind of what that math looks like. I'm definitely not going to go into the details here, but I just wanted to give you a taste that we can make this mapping precise. But interpreting it as a neuromorphic algorithm was the real unique insight, because all of these terms in the equations don't immediately suggest a neuromorphic implementation. But one of the advantages of having the flexibility of the hardware that we have is that we can begin to try different kind of mappings of these terms and these equations to different pieces of the neuromorphic computer that Eric described, and we can actually find an exact mapping to these kinds of mathematics. But importantly, what was found, if we go to the next slide, was that neuromorphic computers are actually quantifiably better at doing these kind of computations than conventional computers. And you can look at the plots on the left if you're curious, but the real finding is on the right. So what we're showing here is a kind of a trade-off between energy and time. So on the y-axis, we have the number of Walker updates or time steps per joule. And on the x-axis, we have the number of Walker updates per second. And you can see GPUs are at the far right corner of the graph, meaning that they're very fast, but they consume a lot of energy. And the red and blue dots are neuromorphic solutions. So True North was an older neuromorphic chip that was invented by IBM, and Loihi represents the first generation of the Loihi chips. And both of these systems show a significant increase in the number of Walker updates per joule, with the number of Walker updates per second, slightly slower, but comparable to conventional CPUs. And so this demonstrates a true neuromorphic advantage for solving these kinds of problems, and shows how the kind of flexibility and strangeness of this hardware allows us to innovate in the algorithm space for coming up with new approaches to problems that we wouldn't think of before, because they just wouldn't be viable on a conventional platform. So with that, I'd like to move to the final slide, just a conclusion. Through a number of different avenues, through machine learning approaches, as well as these random walk approaches and other stuff that we're considering, we believe that neuromorphic computing is a viable path towards significantly more energy efficient scientific computing. But because it's built on different starting assumptions, it requires careful numerical analysis that's often glossed over in conventional architectures, but we have to go back and sort of very carefully think through the math about how the algorithms that we think we understand would be implemented on these kind of systems. But to me, that's very exciting because it means there's a lot of opportunity for novel algorithm development, and the landscape for neuromorphic computing is wide open. So, as I mentioned, we're looking at other kinds of scientific machine learning architectures. We've got, sort of preliminary work on a number of different approaches, and we're really just trying to map the landscape of what's possible with neuromorphic. And these are some of our initial forays that we're very excited about. So with that, I'll conclude, and I'm really thankful for the opportunity to present.
Thank you, Dr. Cyr and Dr. Theilman. It was a pleasure to hear your lecture today. We're now going to move into the Q&A portion of this session. So for anyone joining us online, please ask your questions through the Q&A function at the top of your screen, and I'll try to get to as many of them as possible. So the first question I have for the two of you is, what do you see are the natural applications for neuromorphing in the computational science space?
Yeah, thanks for that. So I think what's really exciting about it for me is, it's a new computing platform, but it brings us into new computing environments, right? So often we might want to do computing in like a drone kind of application for data collection or something like this. And this is hard because we're power limited in those environments. And so the idea that we have an opportunity to really do real computing in a low power environment where we could do real kind of computational analysis, I think can open up some new doorways to different kinds of applications for computation, moving from like a purely HPC driven context where we do big PDE solves or whatever on supercomputer exascale class machine, but now we can solve a bunch of other problems, computational problems, to solve kind of local systems, local problems in the drone or whatever computational environment we might be in. The other side of that coin is, as I kind of alluded to earlier, the power footprint of even big systems could benefit if we can then use these kind of lower power systems, come up with good algorithms, and then use lower power systems to reduce the computational cost. So now that we can have cheaper data centers, and they don't all have to have a power plant sitting next to them like we're talking about today.
Thank you for your response. So our next question comes from Mark. And Mark asks, for someone who's intrigued with neuromorphic computing, how or where can I learn more in relation to my industry and how this can apply? I personally find relating to my area of familiarity advances my knowledge, expanding it from all the information you've provided.
Sure, that's a great question. So because neuromorphic computing is, the term has been around for a while, but the field is sort of in this state where there isn't, a single answer to the question of what a neuromorphic algorithm is. And it's going to vary, as we've seen in different contexts. Different approaches might use the features of the neuromorphic computer in different ways. And so one of the things, actually, we talk about this a lot, is that it's hard for me to point to a single source and say that's a good place to learn about the state of neuromorphic computing, for better or worse. I think that's partially exciting because we're sort of still defining the landscape, but it also makes it hard to get people on board with where we're at, which we'd love to do. We'd love to get, as Eric mentioned, he's a computer scientist by training. I'm a neuroscientist. It's a very diverse field, and we really want to bring in people with different kinds of expertise to kind of take a look at what we're doing and offer ideas about what how what we're doing kind of resonates with them. I will say there are several review articles that have been published recently that offer a good overview of a particular part of the neuromorphic computing landscape. And I've noticed that there's starting to be more YouTube videos that describe it. So, searching for, especially, like with the release of these larger systems like Hollow Point, more people are starting to talk about it and provide their take on it. So I've seen some YouTube videos. If you were to search neuromorphic computing, there would be several that pop up that I think give a reasonable overview. But I don't have a great answer for that yet, because we're still kind of defining the field, I would say, in some sense. But my best advice would just be to pick some angle at it and start reading and just dive in.
Maybe I can add one thing to that.
Yeah.
So I know, like, that within spiking neural networks in particular, if that's an angle that you're interested in, there are several pretty good tools for spiking neural networks that are built on modern neural network software platforms like PyTorch. And I'm happy to send you those. SNN Torch is the one that I'm most familiar with, but I know that there are several others.
Thank you. Our next question comes from Richard, who asks, does the accumulator only take input from the processor? Can it receive historical learned data from external applications?
Brad, do you have an answer for that?
Well, yeah, so that's a maybe a little tricky question, but I guess what I'll say is that there's the accumulator itself. Like, if you were to separate out the connections from the accumulator is extremely passive. It's just, whatever this weighted spike train that's being provided to it from several neurons, it's just going to dump them all into the same place. Where the real degrees of freedom are in the weights themselves and in the parameters that describe how that state evolves. So as Eric mentioned, these individual neurons act like dynamical systems. And so part of what we're thinking about is like, well, if we implement different kinds of dynamics within those dynamical systems, that effectively amounts to using past information in different ways. And that's tricky, because that's very different from how we normally think about programming computers, but it's also very powerful because this sort of recurrence that allows us to feed information back to itself allows us to kind of, I would say, put information in a higher dimensional space that we can then use later if we understand how to kind of extract it correctly. And then also, of course, I mentioned the weights. So one of the things that we didn't talk about in this talk is plasticity. So plasticity refers in neuroscience to the way connections between neurons can change. And these computers can also emulate those processes. So one of the things that we haven't explored terribly deeply yet, but we're starting to get into is, Luigi and all of these other chips incorporate plasticity rules into the architecture, which means that the values of these state variables and the spikes and the weights can all be combined to produce updates to the individual weights themselves. So that means that the network can modify itself as it's running. And that's a very powerful mechanism for incorporating past information into the structure of the network, so that things like learning and incorporating new data can be realized. But one of the difficulties is that our best algorithms for learning in machine learning are based off of, for example, backpropagation, which requires differentiability. And the biggest challenge is that because neurons communicate with spikes, which are discrete events and therefore not differentiable, the backpropagation algorithm itself doesn't apply directly to these networks. And so that's actually a huge part of neuromorphic research, is how do you define learning rules that work in this under these constraints?
Thank you, Dr. Theilman. Our next question comes from Robert, who asks, could conventional neural networks use lower precision to save power and still work?
Yes. In fact, but there's like a lot of research in quantization, which is basically turning conventional neural networks to use fixed point kind of arithmetic and these kind of things. But there's even been this really recent and I think fairly exciting article from the the spiking neural network community, where they said, oh, instead of using weights in a matrix that are kind of floating point numbers, how about we just use binary, like 1, 0, or -1 operations? What that does is it eliminates the need to do any multiplication, which saves a great deal on power, potentially has a great deal of power savings. And they actually showed that they could do some sort of language modeling tasks here. So I think that's a really great frontier. I know quantization has been really important historically, especially in neural net inference with neural networks. And so these things all play a really substantial role in controlling the power.
Great, thank you. We have another question from Richard. And Richard asks, how do neuromorphic systems compare to traditional application-specific hardware in relation to solving cryptographic solutions?
So I know nothing about cryptography. I know that there's a lot of work in FPGAs, and I think there's like a lot of similarity with the FPGAs in terms of kind of a data flow style model. Yeah, I can't speak directly to the cryptography application. I know that FPGAs are useful and often used to test neuromorphic ideas. I don't quite understand the power comparison trade-off there. Brad, I don't know if you have anything else to add to that.
Nothing to add to that.
Thank you. We now have a question from Patrick, and Patrick asks, this is a long one, in the spiking neural network versus neuromorphic algorithm comparison, it seemed like you were forcing the neuromorphic data into a representation compatible with what you'd get from a spiking neural network. Do you think there'd be a more natural or optimal way to do it if you didn't have to copy over the approach from the spiking neural network? If so, do you believe all your conclusions would still hold?
The presentation I gave was very much a purist presentation. If you actually look at the hardware implementation, the information transferred between, say, neurons isn't just a spike, okay? In a sense, like 1 wire and 24 wires is not that different. And so we could have more information transferred in between neurons with that additional kind of width, precision. What I will say is that it's still critical that we have situations where we can turn off those communication pathways, where we can say, oh, no information is being passed down there, because that increases the sparsity of the computation. Basically, the amount of information being transferred is less, and that could potentially translate directly into power savings. But yeah, I think that there's some relationships here that we can kind of exploit to kind of maybe broaden the applicability of the kind of computational models. But I think the general idea of flowing information over kind of neurons as opposed to neurons reaching out to get information, I think that's going to be kind of a persistent thing. And we're already seeing that in some of the data flow architectures in other contexts. Brad, did you have anything you wanted to add or disagree with there?
No, I think that's a pretty fair answer. I'd say coming from the neuroscience field, I mean, one of the major questions in neuroscience is this question of what is the neural code, if such a thing exists. And as I mentioned, there's not really one answer. So in our case, the approach that we picked was the one that was the most sort of mathematically tractable. We could start to prove theorems about information represented in this particular way. And now that we have some experience with that translation, we can start to see, well, what if we change this a little bit and kind of, learn like as Eric mentioned, sparsity of the computation is important, super important for power savings. And so, now that we have this sort of grounding that we can start from, we can maybe tweak our encoding and decoding representations of the information in ways that increase sparsity, improve energy efficiency. But I don't think that the overall conclusions will change, because the idea is, as you mentioned, you're only transmitting information when it matters, and the question is defining what when it matters means. That's ultimately what the mathematics we described was. The operations that are implemented in a neuron below the threshold, meaning before the neuron spikes, are sort of irrelevant from the point of view of other neurons, because all the other neurons see are the spikes. So if we can sort of separate that as much as possible and just get the information transmission between neurons as sparse as possible, then we can just say, like, okay, well, what do we need to produce that particular spike train? And that seems to be the kind of the path forward based on what we started with here.
Great, thank you very much. We have another question from Robert, and it's a follow-up to his previous question. He asks, could you make neuromorphic computers with high precision floating point numbers if you're willing to use the extra power?
Yeah, you could, but I think that incorporating floating point units would, it's like a chain is only as strong as its weakest link, right? So if you include those energy demanding components, you're going to kind of kill any sort of neuromorphic advantage that spike-based computation is going to give you. One of the things that that people are looking at that's sort of related to what you described is to not implement the neural computations with digital CMOS architectures, but actually use analog circuits. And so you could argue that that's a kind of floating point, because you're replacing these integer values that are being passed around with actual continuous physical quantities. Like, so the membrane voltage in the Lewy neuron becomes the actual voltage on some electrical component. And that is a very promising approach, because that's even more energy. Analog approaches can be even more energy efficient than the digital approaches. And so if you combine that intrinsic advantage with the advantage that you get from this sparse computation, we think you can get even further towards truly brain-like energy efficient computations. But the problem is that designing these analog circuits is very touchy, because they're noisy, the components drift, and have imperfections. But the same things are true in the brain. I mean, the brain is an analog system fundamentally, and it seems to handle this well. So we think that there's a lot of opportunity for even bringing in more biological realism to these neuromorphic systems through analog computations that we still haven't fully explored yet. But these digital systems provide us a really convenient way to test out algorithms and neuromorphic approaches that could maybe one day look, like be implemented in an analog circuit.
Great, thank you very much. We don't have any questions left in the chat, but I did have one personal question that I wanted to ask. I was curious, when you're talking about hollow point and how it's only, I guess, kind of about the approximate of an owl brain, are there any reasons why there isn't something bigger? And maybe could you share some of those limitations?
Well, so that's a good question. I mean, it touches on the real computer engineering of this kind of system. One thing that I mentioned is that the system consists of basically 1,000 separate chips that have to kind of talk to each other. And if you look at actual brains, like you take a brain and you slice it up, the wires in the brain are so densely packed that neurons can. You can have a lot of neurons that can communicate across long distances, but the system is so densely packed that the latency and these sort of other kinds of things you have to think about are not significant. Whereas, when we're building these, engineered systems, you typically, our wires are on a very specific grid, and they can't, kind of not like they can't jumble around as much as you see in the biology. So that places limitations on what's called the fan out and fan in, which are the number of neurons that a neuron can talk to or can receive from. And so I believe that's probably one of the bigger limitations to going bigger. But these are problems that people are working on and are actively trying to solve. And the other problem is that since we're still evaluating neuromorphic algorithms. We don't know what the optimal connectivity exactly is. So these systems are built to be as flexible as possible so that we can try different kinds of architectures. And if you try to, accommodate everything, you're obviously gonna have to make trade-offs. So, as we understand more like what specific architectures are going to be really powerful, then maybe we can design systems that are a little bit more tuned to those architectures and even scalable to even larger sizes.
Great, thank you so much. I haven't
Thank you.
received any other questions in the chat, so I think that will conclude our Q&A for today. I wanted to say thank you on behalf of everyone who joined us, to both you, Dr. Cyr and Dr. Theilman. We really appreciate you sharing your expertise on neuromorphic computing with us. For everyone who's joined us today, if you enjoyed this lecture, I wanted to remind you that our other lectures are also available through ATCO's YouTube channel. And that concludes our lecture for today. Enjoy the rest of your afternoon, and thank you for joining us.